Oh my gosh.
I'm feeling lazy today, so I won't talk.
Move around on the chair. Yeah, you don't even have to stand.
I won't talk. I'll just, if students complain about lecturers reading slides, so I won't be reading. I'll just be showing.
No one will complain about it.
Anybody? Well, people complain about me.
People complain about it.
The dean.
The
This is in kilopounds. Kilopounds means that it's thousands of pounds. Like kilobytes. Kilopounds is like kilobytes.
Did it kill you? What is kilopound?
Or kilograms.
Oh,
Kilograms
it's
are
not.
thousands of grams, so kilopounds is thousands.
Oh, yeah.
No, they're doing this for the tip again. So what am I supposed to do? I can't remember. I remember we discussed something. Come on, guys. Hello there. Thank you. Okay, so that's the problem. So now the main question really is, what are we doing this term? And what we're doing this term is integer linear programming. Linear programming, you know. Okay. So what is a linear program? It's you get some decision variables, and there is an objective, which is a linear function of the decision variables. And then there are some constraints, which are linear constraints. So that means I take a linear function of the decision variables, and that has to be less than, greater than, or equal to a number. Now, integer linear programming is just like linear programming, except it's not, because you can add the constraint that all of them, the decision variables, have to be integers in the solution. And it completely changes the problem. It completely changes the difficulty of solving it and so on. So solving a linear program, which is what we've been doing for a year now or so, it's just a small, little, easy subproblem when you're solving integer linear programming. These are the things. And what we're going to do? Well, there are two kind of big topics in linear programming that we did. Well, maybe three. In the first year, we did two things that were quite distinct. One of them was doing the simplex method and all that, which was really solving. When you get a linear program, how do you solve it? And the second bit was when you get a quasi real-life situation, how do you make it into a linear program? So this kind of formulation bit. So that's going to be the same with integer linear programming. We'll look at some methods of solving them, and we'll look at some situations. And actually, there are loads. Any problem you can think of, almost, can be formulated as an integer linear programming problem. So we'll look at many of them. And that's the plan for this term. We start easily, so we start by looking at this. Have you solved it yet? question is, well, we've got three kinds of containers. Each of them has a different weight and a different income from transporting it across the ocean. Your ship can only hold 45 tons at most. So you can't take everything, because if you took 24, 55, that's already way wrong. So you have to choose how many A's, how many B's, how many C's you take. And you want to maximize your income, obviously. So that is the question. Keep solving, I'm just writing something. You found it? Can anybody get at least 20? But that's 4 A's, for example, and 1 C, that's still okay. A 3 C, that's even worse. Okay, so you could say C is the best because it's 7. So if you take 3C, you can't take 4. If you take 3C, you get 21. But,
You can't take any B, so you have to take an A. 25.
Yeah.
Okay, so the best must be 25, right?
So because you start with this, so you take as much of, so you take 3 C's, and that gives you 21, and there's 9 spare capacity, so you can't take any of B, but you can take 1A, so 1A, so that gives you 25.
3 A's and 2 C's.
Oh, 3 A's, 2 C's. That gives you 26. How about 2 A's, 3 B's? That gives you 26 as well. We can't really, it's kind of hard to prove that you can't do any better, other than looking at many different possibilities and seeing that they're not better. And that's the problem with interlinear programming, because nobody really knows whether there is a better way than looking at lots and lots of different combinations. And like in linear programming, you don't do that. You just but this, nobody knows in the whole world. Probably not. It's very, because like, people do it. It's not a joke. I mean, this is a joke. In reality, there's what the computers do. They keep solving interlinear programs all the time. People do it, and it's everywhere. So they've been looking at how to solve it as efficiently as possible, and nobody really knows any easy good way that would always works. Be really fast. We'll see what we can do. Okay. When I started writing is now you forget these containers are indivisible. You take a 7th of a container. Then this looks like an easy linear programming problem. You can say how many of A, B, and C you take. You want to maximize the profit, which is simple. You can't exceed the capacity, so 6xa plus 5xb plus 6xc can't be more than 45. And you can't take more than 4 A's. You can't take more than 5 B's, and you can't take more than 6 C's. And you get an integer, sorry, you get a linear programming problem. Great. Well, if you solve it, have you done the simplex?
Should the constraint where it's less than 45 not be 6, 11, 12?
Sure. Thank you. Yeah, so just before leaving my office, coming here, I was looking for that white erasing, deleting stuff, and I couldn't find it. And then I said, well, okay, yeah, that. And then I thought, well, I'm not going to make it. And here it comes. I think you can read it. I think the student who asked for it is not here anymore. Anyway, the optimal solution is XA is 4, B is not, and XC is 7/4. And the optimal objective is 28.25. Okay.
Can you take like 3/4 of a container?
No, that's the problem. And that's exactly what I said. So think of if this wasn't here, you could take 3/4 of a container, and this will be the solution. But it's not. And you can actually see, well, what we're getting is better than the 26 that we were able to get by using antigen. Well, of course, it's better because you're removing a constraint on something. The solution can't get worse. We can already see that the optimal solutions that we got there is true. Yeah, I promise you they're not true. If you find a better one. If you find a better one, I'll give you a Kiwi dollar.
Keep it.
Yeah, ready? In a way, you can see that just solving the linear program and then somehow rounding the solution or something like that. There's no way of solving it because this is nowhere near that. Not really do that. So something more sophisticated will have to happen. Well, before it does, I want to finish it. So this is no good. But now we're going to allow a new sort of constraints which will say that all of these have to be integer numbers. The Z is integers. Did you learn that from first year? It comes from the German word Zahl, number. In German, all numbers are integers. Okay, so if you take this objective, these constraints, you get something that's called an integer linear programming problem. This and this is called an integer linear program. And that's the kind of beast that will be solved. Have I been wasting time efficiently? Yeah.
Okay, let's say this is XA, and this is XB, and we have 1, 2, 3, 4, 5, and here we go. Okay, so this is a picture when there's no XC. So what do we have for constraints? We have one that says that XB is less than or equal to 5. So you have to be down there. You have to be up there because XB is non-negative. How about XA? XA is no more than 4, is it?
Yeah.
So there's a constraint that goes like this. You have to be between those two lines. And then there's another one which says that, what, 6XA plus 11XB can't be more than 45. So there's 4 and 1 11s here, I think. Something between 7, yeah, 7.5. No, doesn't. And there's this constraint here. You have to be down there. Okay, so in the ILP, the feasible region would be this. Now, why am I saying XC is equal to 0? Well, because I want to get rid of the third variable because I can't. Not very good at making 3-dimensional pictures. So this 2-dimensional one we'll have to do it for the third one. So if you only have XC equal 1, then the optimal solution is going to be one of the point programming. But actually, what you're looking for is the best dot. This one I don't know. Yeah, it's the one. So the feasible solutions don't form this whole quadrangle, but they're only the dots. So you want to find the best dot. It's kind of hard to do. So one idea how you could do it is, if you knew somehow if someone gave you it's a very simple problem because there's only 2 variables and all that. But if someone gave you this constraint, this green line, then you could solve a linear program and you would know that your solution is actually the same. That the optimal solution of that LP, or at least one of them, would be in the corner, so it would be integral, so that would actually be the thing that you're looking for. Make sense? Okay, I'll say that again. So you're looking for the best dot in the green area, and assume you can solve linear programs. Okay, so a linear program will always give you a basic feasible solution as your optimal solution. There are several. And there's only one optimal solution, and it's going to be one of the polytope. Or there are several,
and then at least one of them is going to be in the vertex. So if you were solving a slightly different linear program, which instead of this red constraint, or in addition to it, like has this green one, which goes through these integer points over here, then your optimal solution would either be this, which is an integer point, or this, which is an integer point, or this, which is an integer point, or this, which is an integer point. But the solution you get would be integrals, and that means that you found what you're looking for. So one idea how you can solve integer linear programs is by introducing additional constraints repeatedly and re-solving linear programs. And then at some point, you'll find that your LP has an integer solution, optimal solution, and then you stop. You have to be careful when you're introducing them that you don't cut off any feasible integer points. And that's called cutting planes algorithms, because they're really planes if you have more than two variables. The other one is just not. Okay? And there's a different way of solving is called branching. So we'll talk about that next time. What did I want to say with this? Okay, I just wanted to give you the geometric idea. The geometric idea of linear programming, polytope, polygon in 2 dimensions, in general, it's a polytope. You're looking for the best corner in that polytope. But here you're doing something else. You're looking for the best lattice point. They're called lattice points. Point with integer coordinates within a polytope. And that's the problem. That's how it's solved. Any questions? Okay. Let's have a look at the second big one. It's a common problem that is encountered in real life all the time. Now, if I say the 2 words that I'm going to say, maximum matching, does that remind you of anything? Game theory?
Yeah.
No. It does remind you of game theory, but this is a very interesting situation. Yes, it wasn't so expensive. Apartheid graphs. I just wanted to point out the ridiculousness of my. No, it doesn't. Does it remind you of anything? Yeah, game theory. No, it doesn't. How can I know what it reminds you of? Anyway, it shouldn't. Yes, it should remind you of bipartite graphs. So if you put, I'll draw the picture. If you put the girls on one side and the boys on the other side, and then you do a bipartite graph, in this case, complete bipartite graph. And all these edges have some weights. So for example, Alice has 0.3 here, 0.7 there, and 0.9 there, and so on. And then the task was to select matching or largest possible weight. So find 3 edges such that every vertex node on this side is incident with exactly one of the 3 edges. Every node on this side is also incident with exactly one of these edges, and the sum of the weights is as large as possible. So some of you probably remember it. Don't. Because we won't do it again. But I don't know. Anyway, this is what you did last year. One way of solving this was using flows. Sound familiar? Okay. You create a flow by putting an orientation, everything from left to right, and then putting one source, like this, capacity 1, and then one target, capacity 1. And then you find the flow, and you hope that it works. Okay. It's not straightforward that it works, is it? If you could do, yeah, I don't know, you do something like this. Let's not talk about this because we want to do something else. So what we can do instead is to have decision variables. Well, what decision variables? I'll give you a hint. There are 9 decision variables. I'll give you another hint. 3 squared is 9. Okay, so XAP, XAR, XAS, XBP. You get the idea. So the last one would be XCS. The objective is clearly to maximize 0.3 XAP plus 0.7 XAR plus so on. Using the numbers from the table in the right places. The constraints. So we want XAP to be 0 or 1. And 1 will mean that Alice is going to marry Paul. And 0 will mean that Alice is not going to marry Paul. And we also want all the other variables to be 0 or 1. What else do we want? we want Alice to marry exactly one person, or not more than one. So we want this to be 1. And we want this to be 1, and we want this to be 1. We also want Paul to marry exactly 1 woman, so we do BP plus X, BP plus X, CP to be 1, and there are 2 more like this, which I'm sure you can imagine.
You need to do the side problem.
You do need to do both sides.
It's a fair side, not just one side. Just saying every woman knows one and you doing the same way.
Not necessarily. Okay, so
In my family,
no.
would be
So what you no, if you didn't have this, it could happen that you have this one, this is 1, and this is 1. These are all zeros. There's nothing stopping you doing that. Okay, so Paul would marry 3 of those in your solution. So you really need to have this. Okay, so that's the formulation. I think that's everything. Okay, is this an integer linear programming problem? Why? Because
It's all the integers.
yes, but is it only linear involved? This is an integer problem. Why is it linear? Because I'm writing this. It's not. The answer is it's not risky because XAP, constrained that XAP is in the set 0 or 1, you can rewrite as XAP is greater than or equal to 0 and XAP is less than or equal to 1 and XAP is integer. So in an integer linear program, what is allowed is only linear constraints, linear inequalities, and can require that the student variable only takes on integer values. Strictly speaking. But because saying that a decision variable can only be a 0 or a 1, 0 or 1, can be written in this way, I think that this is fine. That's actually quite common in many applications that you want decision variables to be binary because they're like this whole binary. There are quite many problems where you want to switch something on or off. So this is called binary.
Any more questions? So what have we learned today? More or less that there are things that look like linear programs, but they're not because they have some integrality constraints. And they're quite common, they're quite hard to solve, and they can be useful. So that's so next week what we'll do is start here and see how we can find a simple example. But I want to demonstrate the principle of how looking for integer, in this case binary, solutions looks like. That's it for today.